In this video, we're going to continue our examination of integration applications with a very awesome application of work. So you might remember work from your physics class. The key identity that we want to refresh is that work is equal to the force times the distance. This basic formula assumes that force is constant as you move an object, and so you're frequently used to using just numbers being plugged in. But what happens if force is a function of distance, i.e. you vary your force as you move? That's very common. So a simple idea is just when you exercise. Are you running with exactly the same speed? Are you exerting exactly the same effort at every moment? Definitely not. It's a function of your distance, right? So we're going to extend our idea of how we can find work with the assumption that force is a function of distance. So let's go ahead and call our force function f of x, where x is measuring distance. Okay, so to remind us of the units, work typically measured in newtons, and yikes, nope. Force usually measured in newtons, distance usually measured in meters. So work is technically a Newton meter, but we have a fancy name for that. We call it a joule. Okay, so how are we going to handle this? Well, what happens if we view the distance as something we can partition? So we'll partition the distance AB into, you guessed it, subintervals, and we will look at the work that is applied on the ith interval. So work on the ith interval is going to be f of x sub I star. This is some point in your ith interval. Okay, because we have to assume that force is only constant at a point. We're making that assumption. We're having an asterisk in there. As we know, we're going to let our intervals go to infinity, so that the width of the intervals is going to go to 0, and that asterisk will go away. So force times the distance of x sub I star the force times the distance would be x sub I minus x sub I minus 1, which is equal to delta x. So the work on the ith interval is f of x sub I star times delta x. If we want to find the work on A to B approximate, it would be adding up from 0 to n minus 1, where n is the number of partition points. And to find the exact work, we're going to do the same thing we've done before. We're going to break our interval into infinitely many subintervals. As n goes to infinity, our delta x goes to 0, and this becomes the integral of f of x dx from A to B. And this is the formula that you're going to see popping out at you in a physics textbook. But this is where it came from. Pretty cool. Okay, hopefully at this point we've seen enough of these examples where you're starting to feel this common thread in the thought process of having an interval and assuming that something's constant on that interval using this like asterisk concept. And then as the interval actually goes to a width of 0, that assumption becomes reality that you are actually constant on the interval, because the interval is just like one point. Okay, let's take a look at an example where we're doing work. We'll start easy and then we'll go to some harder examples of work. Okay, so when a particle is x meters along the x-axis, a force of 20 over x plus 1 newtons acts on it. Find the work done in moving the particle from 2 to 3 meters. Okay, so I can see my integral popping up here. I've got from 2 to 3, and my force function is 20 over x plus 1, and we're integrating with respect to x. So when I integrate this, I get 20, it looks like, oh, got my ln, that looks like my ln function, ln of x plus 1, evaluated from 3 to 2, which is 20 times ln of 4 minus ln of 3, and sometimes you'll notice in textbooks and other places that they'll use log rules to condense this to a single logarithm. You don't need the extra parentheses there. So it would be 20 ln of 4 over 3, and unit being joules. Sorry, I realize I should have written lowercase j for the joules. Lowercase j for the joules. Make changes if you wrote that down. Okay. Pretty straightforward. So let's get a little bit more spicy here. What if we're trying to find the work of pumping something? So technically when we pump liquids out of containers, or we're pumping in, just pumping in general is a work calculation. So we're going to do the setup within the actual examples here. So let's say we had a cylindrical tank with height 6 meters and radius 2 meters. It's half filled with an oily BP product whose density is given by, okay, so here's our density function. F of H equals 140 minus 0.2 H kilograms per meters cubed, where H is the height above the bottom of the tank. We need to find the work required to pump the oil to the top of the tank. Okay, so this example is a lot harder than the other one, right? Okay, let's break down our formula. We'll find the work to pump one bit of the material up. So that'll give away the concept. So let's break down our work formula. Okay, work equals force times distance. Okay, but what is force in this case? That's a really interesting question because it's not as easy as in the last example where we had a force function. We are not given a force function here. We're given a density function. So that's because density of the liquid is going to affect the force that it takes to actually pump. So the force for pumping, let's say, across a constant height is the volume color code it, is going to be the volume times the density times gravity, which we're going to denote with a G. And we're assuming that density is constant on a slice. I shouldn't use rho here because this problem uses F for some reason, so we'll just say density in words, okay, times the distance. Okay, and we're assuming gravity is 9.8 meters per second squared. This is the work one, we'll call it slice of fluid. Okay, so how we're going to do this, let's get our picture going, and we'll work on breaking our tank up into intervals. Okay, so our tank is height 6 meters, height 6 meters and radius 2 meters. And it's half filled, so it'll be filled to a height of 3. And what we're going to do is, let's say we took this interval from 0 to 3. So it says the height, h is the height above the bottom of the tank. So h equals 0 here. H equals 0 here. So if I take this liquid and break it up into slices, I'm going to choose just one random slice. We're going to assume that on this slice, the density is constant. Okay, so this is height h above the bottom of the tank. Height h above the bottom of the tank. Okay, why did I say h? Because they gave us that variable h within this problem. Okay, so the density, we're going to assume that it's constant given by this function at this h value point. So the work to lift that slice is going to be given by the volume of the slice, which is pi times the radius, which is 2, times the thickness, which is delta h. Okay, why is it a delta h? Because it has thickness, a difference of h values. Okay, pi radius squared delta h, that's the volume, times the density given by f of h. That function, we'll fill it in a second, times gravity, times the distance to pump it out of the tank. So this is the distance you're covering work on. So what distance do I have to lift this water out? Let's color code that in red. I have to lift this, and it's not water, it's oil, but my bad. Okay, so the distance I have to lift that slice out is going to be not h, but 6 minus h. Okay, so a lot of pieces of the puzzle, but this is the work to lift just one slice of fluid out. So if I wanted to look at the work to lift all the slices of fluid out, I would go ahead and I would add up pi, 4 pi, f of h, g, 6 minus times 6 minus h times delta h. And what am I letting go to 0? The number of slices of fluid, which is contained within that delta h. So as I let the number of slices go to infinity, delta h is going to go to 0, and we get the work to lift all oil. The exact formula is going to be an integral, you guessed it. In this case, it's going to be 4 pi. F of h is, in this case, (140 minus 0.2 h) times 6 minus h times g. We're integrating with respect to h. The delta h goes to 0. Where are we slicing from? We're slicing h values, and we're slicing from 0 to 3. Okay, and so when you go ahead and integrate, what can you factor out? I recommend that you do all of these integrals using technology. If someone actually said, okay, go ahead and compute that, I would go ahead and do all of them with technology, but I would factor out the 4 pi and the g, and I would just have it integrate the remaining value. Which is going to equal 1886.4 times 4 pi joules. Okay, so before we jump into another example of this, let's take a look at what we did. Okay, so because the work for pumping up the fluid is the force that we apply to pump the fluid times the distance that we have to pump the fluid up, well, obviously the distance that we have to pump the fluid is different. It varies. And the density in this case also varies. So when we look at our work, we had a formula applied for density, but the concept for this problem is always going to be the same. So you'll start off with your tank. You'll start off with this basic formula of work equals force times distance. And the force is always going to be the volume times the density times the gravity. But then you'll just have to fill in, depending on the tank, the volume can be different, the volume of one disc of fluid. Depending on the fluid, the density might be different. Like if it's not uniform density, lots of fluids don't have uniform density. The gravity is always going to be the same. And the distance that you're pumping the fluid, that varies within the problem. So in each of these situations, what you're going to want to do is take a look at your tank, cut a slice of the fluid, and go through this thought process of what's the work to lift one slice. Okay, now that I know the work to lift one slice of fluid, I can figure out the integral to give me the work to pump all of the fluid out. Okay, let's take a look at a more interesting tank shape. So this is a cone. Most people are very scared of cones. I don't know why they're scared of cones in this case, but no need. Cones are fun. Cones are our friend. Okay, so let's say we have McDonald's oil, and it's filled to calculate the work done in pumping McDonald's oil, density 6 kilograms per meters cubed, filled to a 5-foot level from an inverted conical tank with base radius 8 and height 7 meters. Okay, so it's filled to a 5-foot level. Here we go. And when it says it's filled to a 5-foot level, it means when you look at the tank and you look at the oil, this is 5 feet. Sorry, I think that's a typo. This shouldn't be feet. This should be meters. Okay, so that's filled 5 meters from an inverted conical tank with base radius 8. And height 7 meters. Okay, let's say that it was actually feet. We would have to do a conversion from feet to meters, which is entirely possible, but it just wasn't my intent for this example to make you guys also do a unit conversion. Why would we have to do a unit conversion? Well, density is given in kilograms per meters cubed. So meters it is. Meters is our standard scientific unit of measurement. Okay, so here's our picture. Let's look at the work to pump just an arbitrary slice of fluid. Okay, there's our slice of fluid. It's a little disc of fluid. The height, we're going to make h the height from the bottom of the tank, just like the last problem. And when you do that, label your picture, okay? Because there's ways you can make the height be the distance to the top, but it's going to change your entire problem. And I'll say that. Like you can, as long as you start from the setup with your h consistent, you can make it be that the height is the height that you have to pump the liquid, but it'll change other pieces of your integral. So I'm going to stick with the convention that height is from the bottom of the tank. And my picture tells me so. So here's what's going to be interesting about this one. When we go ahead and write our work to pump one slice, the volume of the fluid is going to vary. Okay, so when we write our force times distance. The distance to pump it is going to be 7 minus h. That part's easy. Okay. The volume is going to be a challenging part. So we'll leave that one. Undone because it's going to depend on the radius. The density is easy, going to be 6 because it's uniform. So the density of all the fluid is 6 in this case. And gravity is easy. So now the hard part of this problem, we just need to figure out volume, and we need to figure it out in terms of h. I can tell that volume is going to vary as a function of h because as I go higher up in the cone, my discs of uniform thickness are going to have more volume than at the bottom of the cone because the radius is changing. So let's take a look at the radius related to that variable h. So I'm going to look at my triangle here. Let's do it in red. Okay, so the radius forms a right triangle with the side of the cone. That's going to be a cool fact. So this side is h because the disk is h from the bottom. We want to know what is r, and that's the unknown. What we know about the side is that it's part of a line that has slope 7 over 8. So let's look at this triangle as a part of a bigger triangle. This is a proportional right triangle to the big right triangle, the side of the cone. This side is 7. This side is 8. Okay. Forgive the fact that I didn't draw my cone very proportionally here. I could have done a lot better at drawing a bigger base on the cone. But 7 over 8 is my ratio. So I can use the fact that these are similar triangles to figure out what that r is. So 7 over 8 is equal to h over r. So lining up the similar sides. 7 is on the same side as h, 8 is on the same side as r. Now I have a proportion that I can solve for r. So 7r equals 8h, r equals 8 over 7h. Okay, so now I can go ahead and fill in my volume. Work to pump one slice then is going to be pi times the radius squared times delta h times 6 times g times 7 minus h. That's the work to pump one slice. So the work to pump is approximately going to be given by the sum pi 64 over 49 h squared times 6g times 7 minus h times delta h, and we're indexing from 0 to n minus 1, where n is the number of slices. And as n goes to infinity, you guessed it, the thickness of the slices goes to 0. And we get the integral from 0, height of 0, because you're pumping liquid at the bottom, clear up until a height of 5. And then this becomes, let's pull all the constants out. We have 6 times 64 over 49 gives me 376 pi g over 49 times h squared, 7 minus h dh, and you end up getting, when we compute that, Okay, so let's look at the problem as a whole and walk through that once again. When we're calculating our work done in pumping fluids, we want to have a picture of the tank because the geometry of the problem is very important in informing the different pieces of our formula. So we know the work to pump one slice of liquid is going to be dependent on the volume, density, gravity, and the distance that you're pumping the fluid. So in each situation, the tank shape, how much is it filled, the density of the fluid, those are all going to come into play. And you want to have your picture set up introducing your variable so that I know what is the variable in your problem. So I set the variable by labeling h to be the height from the bottom of the tank. And that carried with me throughout my entire problem. If you set your variable up to be different, like the height is the height from the top of the tank, which some people choose to do, your problem is going to look a little bit different. This is actually my favorite application of integration and the last in the sequence of videos for my channel. In future videos, we're going to be taking a look at how to integrate, so integration techniques. I'll see you then.